Um, okay, so force types. So first, there are field forces. And in this class, that really just means gravity. What are some other kinds of field forces?
Electromagnetic.
Yeah, electric fields, magnetic fields. What? Yeah. So for us, it just means gravity. And then the bigger issue to deal with, because gravity is always just mg down, that's pretty easy to deal with. Then we have the contact forces. And the contact forces are broken up into 4 categories. The first one is pushing contact. The second one is pulling contact. The third one is friction. And the fourth one is spring forces. We've pretty much finished 1 and 2. I'm gonna talk about pulleys a little bit before we go on to friction, but we're basically done with the first 2, and we have the last 2 still to go. So pulling, and let's talk about when cables pass over pulleys or pass through pulleys. And the basic idea is all that a pulley does is change the direction of the force that the cable applies to things. So it changes the direction of the force. The cable applies. So for example, if you have an object hanging over a pulley like this, and let's say this is 10 kilograms. Let's figure out, so this force F, and then let's think of another case where you have that same mass and we're applying a force F2 here. What force is required for this to be in equilibrium? In other words, for the acceleration to be 0. Well, a free body diagram of the block here has a downward force of 10 times 9.81. And an upward force, since all that pulley does is change the direction of the force applied to that cable, the force applied by this cable here is F1, just following the rules of a cable force just going away from this body. And so this free body diagram just looks like this, F1. Okay. Newton's second law then says 0 negative 98.1 plus 0 positive F1 is equal to the mass times, we're assuming that this has no acceleration, so times the 0 vector. And you get that F1 is equal to 98.1 newtons. Okay, what about the other case? So I guess let me number these. Let me call that one 1. Let me call this one 2. So here's the free body diagram of case 1. For case 2, we don't have the pulley. And so we just have the weight force of 10 times 9.81. We have the upward force of F2. Newton's second law now works exactly the same way. We have 0, negative 98.1. Plus 0 F2 is equal to 10 times 0, 0. And you get that that force F2 is the same thing as the force F1. It's equal to 98.1 newtons. Question?
So are we just going to be saying that the pulleys don't have any friction?
Yeah, so we're assuming that the pulleys don't have any friction or any mass, and we're assuming that the cables don't have any mass too. Yeah, it's not super hard to deal with the mass of the cables. Dealing with the mass of the pulleys, it's not super hard to deal with the friction of pulleys. It's a little bit more complicated to deal with the mass of the pulleys. In dynamics, you'll do that kind of stuff. Okay, so the bottom line there is changing the, so all I did by having this supported by a force going over the pulley versus supported by a force up is I just changed the direction. I didn't change anything about the magnitude. Okay, so let's do another example. So let's say we have, let me do it this way. We have a pulley here and a rolling cart on the flat surface. And let's say that the mass of this is 2 kilograms and the mass of this is 1 kilogram. And let's say we want to calculate the acceleration of the 2 kilogram cart. And what's the tension in the cable? Okay. Well, you might think that the tension in the cable is just going to be the weight of this, but we're going to see that that's not true. The tension is going to be a little bit more than that. We'll see. No, a little bit less than that. So a little bit less than that it should be. So how are we going to calculate this? What are we going to do? So one of the key things we're going to do, we're going to isolate each one of these two things, okay? And we're going to come up with Newton's second law for this one and Newton's second law for this one. And then one of the key facts that we're going to use is that this cable applies a pulling force to this, that's equal to the pulling force that applies to this, okay? Because that's what pulleys do if they're frictionless and massless, which none are. But it's usually a pretty good approximation of the answer. Okay, one other thing that we're going to have to do, we'll see when this comes up, is we're going to have to come up with a relationship between the acceleration of this and the acceleration of this. Okay. So how are we going to do that? Well, think about it this way. If you pull this down an inch, what happens to this one? Yeah, this one moves over that way an inch. So if this one has an inch in the negative y direction, this one has an inch in the positive x direction. Okay. And so what if that happens in 1 second? You know, then this one has a velocity of an inch per second in the negative y, and this one has a velocity of an inch per second in the positive x. Okay. And what happens if it goes from rest to a velocity of 1 inch per second down? This one has an acceleration of, so this one has an acceleration of 1 inch per second squared, which is the same as this one going in that direction. So whatever the position change of this one is in the negative y direction, that's the position change of this one in the positive x. And that's true of velocities and accelerations too. Okay. So this one has an acceleration of a in the negative y direction. This one is going to have an acceleration of a in the positive x direction. Okay, so I'll show you where that comes up in this problem, but we're going to have to use that fact. Okay, so let's start with a free body diagram of the 2 kilogram cart. And actually, why don't you do this? Let me give you a couple of minutes. Draw a free body diagram of the 2 kilogram cart, and then I'll do it. Make sure that we're all on the same page with that, and we'll come up with Newton's second law after that, and just build up this problem together. Okay, so the way to do that is you have a weight force down. So that's 2 times 9.81, 19.62. And now go around the boundary looking for the contact forces. There's a pushing contact from the ground on the wheels. And then when you get to the right side, that cable is pulling on it. So that force is parallel to the cable, away from the chosen body. We don't know what the magnitude is, so we'll have to call that T. Okay. And what do we know about the direction of the acceleration of this? Remember, on rolling and sliding problems, we have to figure out whether it's moving in the x direction, the y direction. Yeah, and actually, we don't even care what the sign is. All we have to do is pin it down to x or y. Okay, so let me do Newton's second law here. So Newton's second law says the weight force is 0, negative 19.62. The pushing force is 0N. The pulling force is T0. And the sum of those forces is equal to the mass of the chosen object times its acceleration, which we know is only in the x direction. Okay. And from this, we get two equations. We get an x equation that says 0 plus 0 plus t is equal to 2a. And we get a y equation that says negative 19.62 plus n is equal to 0. So n is equal to 19.62. Okay, are we done? We solve for n. No, that was not what I asked for. It's something, but usually that's not what we want in these problems. So it turns out, I mean, if you were asked for that contact force from the ground, then you're done. Usually you're looking for other stuff. So in this case, that doesn't get us any closer to what we wanted. What about this first equation? Can we solve for anything there? That is the two things we want in it. Are you like, I'm embarrassed for you for even asking that? That's one equation with two variables. So you can't solve for anything. Although it is a useful relationship, we'll see. Okay. So we're just going to have to go on now, draw a free body diagram of the second thing, and eventually hope that we can have a system that we can solve, you know, by substitution or whatever. Okay. All right. So now take a couple minutes and draw a free body diagram for the 1 kilogram. So the 1 kilogram we have the weight force down of 9.81 times 1 kilogram, so 9.81 newtons. And then we have that cable force pulling on it, and a pulling force is parallel to the cable away from the body, so it's this way. Do we know the size of that cable force? We don't have a number, but we know that it's T. It's the same magnitude as the cable force that it applied to the other body. So that's it. And now Newton's second law. We can write this as 0, negative 9.81. Plus 0t is equal to the mass times the acceleration. So now we have to think about the acceleration. There's two ways to do this. One is you can treat this as having its own acceleration and then later come up with a new equation that relates the two accelerations to each other. Or if you recognize it right away, that those relationships are fixed to each other in some way. So we already said that we're imagining that this one has an acceleration a0, okay? So say put a 1 in there. What's the acceleration of the 1 kilogram? It would be 0, negative 1. You have to sort of think physically about how those relate to each other, okay? So can you come up with a relationship involving an expression involving a for the acceleration of the hanging one? If this one is a0, this one is a0, what's the acceleration of this one? 0, negative a, okay? So this we got from, you know, inspection, but just like figuring out how the system, those motions relate to each other. Okay, so the x equation, that definitely isn't going to help no matter what you're looking for. It's reassuring though. And then the second one says negative 9.81 plus t is equal to negative a. Is there anything we can do now? We want the t and the a as numbers. Well, we have one equation for t and a here, and another equation for T and A here. So that's a system of two equations, and we can just solve it by substitution. Okay? So those boxed equations are two equations for two unknowns. And you can do that by substitution. Okay, well, if I plug the first one into the second one, I can just replace the T in the second one with 2A. You get 9.81 plus 2A is equal to negative A. And so negative 9.81 is equal to negative 3A. And so A is equal to positive 3.27. And now this is an important step for making sense out of this. Well, we're also supposed to calculate T. So let's calculate T first, but then, and so plug that back into either one of these. T is equal to 2A. So the tension is equal to 6.54 newtons. Which you can see if this was just hanging at rest, the tension in that cable would be the weight of the thing that's hanging. But since it's accelerating at something less than that, the weight of this is 9.81. That cable tension is only 6.54 because of that acceleration. Okay, but we want the acceleration of the 2 kilogram part, and I gave a value of a variable. An acceleration is a vector. So how do we come up with the acceleration vector from that value of A? Well, notice that we already came up with an expression for the acceleration vector. This is it. You know, that's the acceleration of the 2 kilogram. We just didn't know yet what the value of A was. Okay? You follow that thought process? I mean, we already said there's the acceleration vector once we figure out what A is. So now we know what A is, plug it in, and that says that the 2 kilogram cart is accelerating. So A2 is equal to 6.54. Nope, I used the wrong one. A. 3.27 meters per second squared. Or another way to think of that is in the positive x direction with a magnitude of 3.27. Nope, not always. Because the magnitude is always positive, but they're vectors. And so the signs just indicate a direction. Yeah, so a tension is, okay, so a tension, yes, is a magnitude of a force, and so that's always positive. But if I had asked for the force that cable applies to an object, then you'd have to plug it back into the vector. That's right. Okay, so now I have a question. So there's nothing that says that I had to isolate this one first, right? We just happened to call, say that the direction of this one was A0 because that's the one we did first. What do you think would happen if instead, so we did this problem again, but first we isolated this one. And then when we figured out the acceleration, we just said, okay, well, it's just going to move up or down. So we're going to call that A0. Are you with me on that? Because we didn't call this A0 necessarily because we knew it was going to accelerate in the positive X. We called it that because all we ever do is choose between X and Y, and the sign is going to work out for itself. So what do you think would happen if we isolated the hanging one first, treated that acceleration like A0, then did the second one and said, okay, well, if this one goes up an inch, that one goes this way an inch, so called the other one negative A0. We have our signs backward on those accelerations. Are you with me? Yeah. So we would get the opposite answer for A, but now we have opposite answers in the vector, okay? And so when we plug the negative 3.27 into the opposite vector, we'd end up with a vector answer that was the same, even though our answer for A was opposite. Okay, so let's try doing that. So now do the same thing again. This time, call the acceleration of the 1 kilogram 0A. Okay, so let's start with, I'll give you a few minutes. Draw a free body diagram of the 1 kilogram. And then write Newton's second law for the 1 kilogram too. And then after you have a few minutes to think about it, I'll go through it. So the free body diagram looks the same as it did before. We still know we have a weight force down of 1 times 9.81. And we have a cable force up of T. And so Newton's second law says 0, negative 9.81 plus 0T is equal to the mass times the acceleration. But this time, since we're doing this first, and the way we always think about this is just like, okay, which way does it move, in the X direction or the Y direction? This moves in the Y direction, okay? So I'm just going to call this 0A. Okay. The X equation doesn't help anything. The Y equation says negative 9.81 plus T is equal to A. Okay. And now we'll go to the rolling one. So a free body diagram of the 2 kilogram. Now we're going to have to think of the acceleration of the 2 kilogram in terms of the one that we've already named. Okay. So take a couple minutes, draw a free body diagram, and rewrite Newton's second law. Okay, so there's the cart. There's a weight of 19.62. There's a pushing force from the ground. There's a cable force, and the magnitude is the same as the cable force for the other one. And then Newton's second law says 0, negative 19.62 plus 0n plus t0 is equal to the mass times the acceleration. So now this acceleration of this one has to be in relationship to the first one that we already named. So if this one goes in the positive y direction, where does the other one go? In the negative x direction. So we'll call this one negative a0. So now the acceleration vectors look different. This is the acceleration vector of, that's the acceleration vector of the 2 kilogram cart. And that's all right. The signs are going to all work out if we follow it all the way through. So the two equations here say, the x equation says t is equal to negative 2a. The y equation says n is equal to 19.62. And now we have, again, two equations that we can solve for two unknowns. In this case, it'll be the x equation from this one and the y equation from the hanging mass. So take a minute or whatever and figure out what the values of t and a are. Okay, so if you solve that system, what do you get for t and a?
T is 6.54 millimeters.
Okay, that's the same as it was before.
A is 3.270.
A is negative 3.27.
A is just the number. It's negative.
Yeah. So if you solve that, you get an A that's negative 3.27. It seems backwards, but now plug it into this acceleration vector. Plug it into the acceleration vector for A2, and you get that the acceleration of that 2 kilogram cart is, we have a negative, and then A is also negative. And so the vector is 3.270. Or in other words, it's in the positive x direction with a magnitude of 3.27. Okay. So even though we made a different sort of default direction for this system, as long as the relationship between the two accelerations are right, the sign will work out on its own. Okay. Okay. All right, I have one more question. I guess I'm going to just finish with pulley stuff. And we'll do friction. Well, I guess we'll wait for friction until after spring break. No, wait, we have class tomorrow, don't we? Oh, yeah, I'm getting ahead of myself. Spring break!
And if you want to use stuff tomorrow,
Now you want to learn about friction tomorrow.
of course.
Have you ever heard of pulley advantage? So I just said all this stuff we did today was like all a pulley does is change the direction of a cable force. But you've probably heard at least vaguely that that you can use pulleys to so that you can lift really heavy things by applying relatively small forces. Okay, so if all a pulley does is change the direction of a force then what's pulley advantage? Well, okay, let's think about two cases. One is like this, where we have a pulley and a mass of 10 kilograms. And a force F. And then a second case with a little more complicated setup. So in this one, let's say that we have we have a pulley connected to the ceiling. And then we have a separate hanging pulley that's connected to our 10 kilogram mass. And the cable goes through the two pulleys over this one. What's the force F required here? So let's think of this one as case 1 and this one as case 2. So what's the F required for equilibrium, for a zero acceleration? Well, we started today by talking about this case. So for this to be at rest, what force would you have to apply to that cable? It would just be equal to the weight of this, so 10 times 9.81. So this force would be 98.1 newtons. Okay. So in this case, case 1, F is going to be equal to 98.1. Okay. But let's do the second one. So case 2. And for our free body, here's what I'm going to isolate. You know, you can isolate anything you can put a closed outline around. So I'm going to do all this. Okay. So free body diagram looks like that. Okay. The weight is 98.1. The cable that is part of the surroundings makes contact with our body here. So that's a cable force T. Same thing here. So that's a force T. And that's the end of that free body diagram. So Newton's second law says 0, negative 98.1 plus 0T plus 0T is equal to the mass times the acceleration, which is 0. Solve the y equation, and you get that T is equal to 49.05 newtons. Okay, so with this very specific setup of pulleys, you can require less, and that T is F, okay, because F is just a cable tension. Okay, so with a very specific setup of pulleys, you can make it require less force to hold up a heavier thing or to lift a heavier thing. The trade-off is to lift this up an inch, you have to pull the rope down 2 inches. And you can fit more and more pulleys into this to get more advantage. And it's used a lot of times in different kinds of shipping yards and whatever. If you do this with 6 hang pulleys all in a line, like in a row out like this, you can get it to be 1/12 of the original weight. So that's the idea of pulley advantage. It doesn't really come from the pulley itself. It comes from using the pulley in a specific way. Okay, that's all. We do have class tomorrow. Tomorrow's only Thursday.